Dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Adda, I'd like to welcome you all to our International Physics webinar. And I'm happy to share with you that today is our 27th webinar. And good morning to all here in Bangladesh, and good afternoon to all those who are connected from Australia. So hope you're well and safe from Corona pandemic, and we are passing very bad time, and this is the new experience for all of us. And we cannot actually continue our normal academic program. So that's why we have to start the online program, like online classes, online webinar and seminar. So our Department of Physics, Pabna University of Science and Technology has taken some initiative for online program. We have started our online classes, online seminar and webinar. And in those online webinar, I'm happy to share with you that the physicists from different countries, and those are well-known scientists, are coming as a speaker, and they share their experience and their knowledge to our student. And I think this is very helpful program for our student, so that they can get knowledge from those well-known professors. And this is also a good opportunity for them to know the recent research of this field. So I have already connected today's speaker, and I'm glad to share with you that today I have welcomed you to a joint session between Pabna University of Science and Technology and Australian National University, Australia, Capital Territory, Australia, in nanotechnology. So we have with us here today Dr. Chennupati, Jagadish, Distinguished Professor, Research School of Physics, Australia National University, Canberra, Australia, joining us from Australia through online. So he has already connected with us. So I'd like to welcome our speaker. Sir, good morning and welcome to our webinar, sir.
Well, okay, thank you very much, Pretam. And so I first of all want to thank you for the opportunity to speak to your students. It's a really pleasure and honor for me to really speak to your future generation of scientists and young physicists and young students, and it's a really pleasure for me.
Yeah, thank you.
So as been mentioned that,
yeah. Okay, sir.
So okay, sir, this morning I'm going to talk about nanotechnology, opportunities and challenges. And Pretam, you want me to go ahead and then give the talk, is that right?
No, I need to introduce yourself.
Okay, sure, go ahead. Okay, in that case, go ahead and do that. Yeah, sure.
So thank you, sir. We are very glad to actually host you in our webinar. I know you are too busy with your research. So the aim of this webinar is to encourage our student and motivate our student in this Corona pandemic situation. And as you agree in our invitation, we are very grateful, and I'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology.
Okay, I can start.
So share that we'll introduce our speaker with you all, and then we have a session where our speaker will deliver his speech, and then we have a time where anybody can join with us in our discussion session. So we know that the title of our today's lecture is Nanotechnology, Opportunity and the Challenges. And our today's speaker is Chennupati Jagadish sir. He is currently working as a distinguished professor, National School of Physics and Australia National University, Australia. And if we see his academic background, he has started his academic career from India, and he completed his bachelor degree from Nagarjuna University. Then he completed his master's degree from Andhra University and MPhil from University of Delhi, and PhD also from University of Delhi. And we can see his lot of achievement in qualification. And his professional career, he started his career as a lecturer in electronics and physics at SB College, University of Delhi, India. And then he got a postdoctoral fellow in physics, Queen's University, King's College, Canada. And in this continuity, he's now as a working as a distinguished professor at the University Australian National University. So he has some honorary position. He was a vice president and secretary physical science, Australia Academy of Science, fellow School of Engineering, University of Tokyo, Japan, and overseas visiting professor Anna University, India, honorary professor Nanjing University, China, 1000 Talent Plant, Professor, University of Electronics Science and Technology of China. And research interest, neuroscience and neurotechnology, compound semiconductor technology, compound semiconductor optoelectronics, compound semiconductor material science, high efficiency compound semiconductor, photovoltaics. And we can see his honor awards and recognition and his fellowship, lots of fellowship, and he worked as editorial, lot of journal. And his professional scientific society leadership, you can see this membership and publication. He has some books and lot of publication. And if we see his Google Scholar ID, we can see his citation number is more than 25,000. This is a great achievement. And also his research grade point is 48.41. This is a great number. So we feel proud and honored to host him as our main speaker in our international physics webinar. So, sir, I would like to welcome you again, sir. It's your time. You can start your session, sir. And thank you, sir.
Well, okay, thank you very much, Dr. Das. And so thank you very much. And so once again, I want to thank everybody for the opportunity to speak to you. And good morning to all of you. And this morning or this afternoon, wherever you are, and so I'm going to talk about nanotechnology and opportunities and challenges. So really, if you have any questions, has been mentioned that I am from the Australian National University. If you have any questions, feel free to send me an email. And if you are feeling shy to ask me the questions after my talk, but if you are most welcome to ask me questions after my talk as well. So here is an overview of my talk, and I'll mention about what is nanotechnology, why nanotechnology is important, how to make nanostructures, some examples of nanotechnology, and also I'll talk about nanotechnology for cars. And so this is, I happen to give you this talk for a car club, which is an antique and the vintage car club. In fact, this is my car, which is a very old car, and in fact as old as I am. And I'll draw a summary for this talk. So before I proceed further, and I just would like to let you know that Professor Rick Smalley, who is unfortunately no more, and so Nobel laureate for chemistry in 1996 from Rice University, and about 20 years back, and he brought together experts in nanotechnology and then asked them the question, forget about nanotechnology, let us identify what are the humanity's top 10 problems for the next 50 years. They've identified energy as one of the top issues which we need to address, and then water, food, environment, and poverty, terrorism and war, disease, including pandemics, and education and democracy and population. And these are the topics which they've identified as the key problems. And as you can see, the energy always comes out to be number one issue. As you know that in 2012, the world population is about 7 billion people, and of course it's growing very, very fast. By 2050, we're expecting that the population will increase to 8 to 10 billion people or so. And so then 2012, we were using about 17 terawatts of energy. By 2050, people are predicting that you need to have 30 terawatts of energy. So that means if we start using fossil fuels, and then we are going to create a huge amount of greenhouse gas emissions, and then the global warming and all of the problems will start coming up. And also it has got a huge impact in terms of pollution and also ruining the health of the people and a range of things. So that's why we need to really develop new technologies which are not dependent on the fossil fuels and renewable energy technologies, so that we can be able to meet the energy needs of the world. And that's something which has been discussed at that time. And I'll try to cover how the nanotechnology can potentially help in the energy sector, and then in what way it can contribute to it. So what is nano? And what is nanotechnology? So nano is whenever people ask you the question, and we say what is 1 billionth of a meter. So when you say 1 billionth of a meter, but sometimes people find it difficult to know what is one sense of what is a billionth of a meter. Well, you can say that you can also call it as a 1 millionth of a millimeter. And so really, just to give you some idea of the dimensions, an ant is about 5 millimeters in size. Dust mites are about 200 microns. So that means 1 billionth of a meter. And human hair is about 10 to 50 microns wide. And then the red blood cells are about 2 to 5 microns wide. DNA is about 2.5 nanometers in terms of its dimensions. And 5 atoms of silicon and will form into 1 nanometer or so. So you can also give you some examples of carbon nanotubes, typically are about 2 nanometers in diameter. And then also if you some of the head of a pin is about millimeter or so. So really just gives you, you're really talking about the atomic scale. I'm talking about 1 nanometer is about 5 atoms of silicon. So really we're talking about atomic scale. So that's why I sometimes call it what is nanotechnology. I call it as engineering at the atomic and the molecular scale. So you can take the planet Earth, and if you shrink it by a certain amount, you get a tennis ball. You take the tennis ball and then shrink it by the same amount, and then you get into the nanoscale of the atomic level structures or so. Here I'm also showing you some Lego blocks. As all of us know that you can take Lego blocks and then build whatever the structure you want and whatever the shape you want by essentially putting the right kind of Lego blocks in the right place. But unlike Lego blocks, in the case of nanotechnology, what we do is that we use atoms and molecules like Lego blocks, and then we can be able to create any structures which we would like to have. So that's why I call it as engineering at the atomic and molecular scale. That's what is nanotechnology about. But because nanotechnology is a multidisciplinary field where physicists and chemists and biologists and engineers are all working together, so sometimes depending on whom you talk to, different people will give you different definitions. And but at the end of the day, it is a very much of a multidisciplinary field. So why nanomaterials are so much interesting and why nano is so interesting? It turns out in the case of nanotechnology or nanostructures, there is a large surface to volume ratio in terms of the dimensionality. For example, I'm just giving you an example of a carbon nanotube schematic here, and you can see all the atoms are on the surface. If all the atoms are on the surface, so then they'll be very good for catalysts. If you're using the right kind of materials in the nanotube form, and then they can act like a very efficient catalyst because all the atoms are reacting with the surrounding medium, and then you can have the chemical reactions much more efficient. Or otherwise, these nanostructures could be used for sensing. For example, people have used carbon nanotubes for sensing of biological molecules or chemical molecules or so. But also in carbon nanotubes, there's a huge amount of space that could be used for hydrogen storage because hydrogen is seen as a clean energy source, and which I will come back and tell you, and then how people are trying to store hydrogen in the gap in this carbon nanotube which you've got. But also carbon nanotubes, for example, are lightweight and high strength. So that's why there's people are very much interested in using these things, really build the high lightweight structures, which are huge structures or so. But in addition to these carbon nanotubes or so, which I'll come back to, but also nanostructured surfaces also have different properties. In this case, if you go and look at a close-up of a particular structure, you can see that close-up, in this case, you end up having some sort of a bumps. These are so-called nanoscale bumps. And these nanoscale bumps or nanostructured surfaces have got different properties than a bulk material, which I will come back and tell you, and what these nanostructured surfaces behave, how these nanostructured surfaces behave. But also that when you go to the second thing which happens when you go to nanoscale is quantum size effects come into picture. So here is a case where I'm giving you an example of cadmium selenide semiconductor. And then when you go and look at it in the bulk form, it looks very much of a grayish color. And you really don't see much of colors in this one. If you take the same cadmium selenide and then make into nano-sized particles, and then if you shine UV light and look at the light coming out of these ones, as you can see, you can get all sorts of colors of light, from red and the green and the blue and purple and whatever the colors you want. You should be able to do that one by essentially changing the dimensions of these nanoparticles of this particular cadmium selenide which we are looking at. So really, the classical physics cannot explain how a material, which by essentially changing dimensions, is change its color. And that's where the quantum physics comes into picture. Essentially, you can, because many of your students are physics students, and you can really do this, the Schrodinger equation and then solve it a particle in a box. And then it really shows that whenever you are reducing the dimensions of this box, and then energy levels of the electrons or holes will start changing. And in the process, you can get different colors of light because the electron hole energy level time energy difference is different depending on the size of these structures. Because of the fact that the quantum effects are coming into picture, people started calling these as quantum dots or nanocrystals or nanoparticles. An important thing is that in this case, you have the quantum effects, particularly you go to nanometer scale, then only you see these quantum effects also, which I'll come back and share with you much more details. And in fact, this work, which has been going on for about 20 plus years or so, now has led to already commercialization. And then nowadays you can go and buy in the marketplace from Samsung and other places quantum dot televisions. Essentially, these quantum dots really emit a bright light, and also you get a high resolution display. So that's why people are interested in using these quantum dots for TV, so that you can get a much clearer and a much brighter picture or so. So really, these nanoparticles or quantum dots could be used for solar cells, or displays, or electronics or photonics applications. These nanoparticles or quantum dots, which are emitting these colors of light, can also absorb the same colors of light as well. So that's why they could be used for solar cell applications also. So why is the nanoscale so interesting? In fact, living things, are assembled from nanoscale components. So a major question addressed by nanoscience is, can we learn from nature? For example, here is an example which I'm giving you of a butterfly. All of us have seen butterflies, and also different butterflies end up having different colors of light to be reflected from them. So you ask the question, why different colors, different butterflies have got different colors of light? Is it due to the fact that they got different chemical pigments, and so that's why they end up emitting different colors of light, or something else is happening? People have looked at the wings of these butterflies in the electron microscope. You can see the porous structure within the wing material here. And if you go and look at the close-up of this one here, you can see that the bone material, air gap, bone material, air gap. So that means essentially light gets reflected because it acts like a constructive interference of the light which is been reflected from this one, so-called a Bragg reflection, whenever the optical path length is equal to each other in the case of the bone material, and then the air gap here. So that matches with each other, then light gets reflected and interferes and then reflected. So that's why you end up getting different colors of light. So essentially, butterflies are showing us that you can create color without pigments, essentially by changing the ordered structure. And essentially, sometimes people call these things as structured colors. So in fact, these are things which you can use it for photonic crystals and a range of applications. In fact, you can treat this wing material like a one-dimensional photonic crystal or a Bragg reflector. That's how end up creating different colors of light by essentially changing the thickness of this bone material, and then the air gap between the bone materials will give you different colors of light. So you can see now you can suddenly start creating color without pigments. And smaller things generally provide enhanced performance. For example, computer chips. So as you can see that as and when we are reducing the dimensions of the transistors, you're able to pack more transistors. So that means you can really create a more highly dense memory. And also you can switch on and off of the transistor much quickly because of the fact that these are of nanoscale dimensions. So electrons don't have to migrate long distances. So that's why you can also create a fast computer chips as well. And lots of many small nano devices are used for faster communications, and also higher efficiency is expected from these nanostructured things. That's why people are interested in exploring the nanostructured materials for a range of applications. So do you remember this particular structure which I showed you earlier? In fact, this is a close-up of a lotus leaf. And all of us, we see this lotus leaf all the time. And so basically, if you put a droplet of water on the lotus leaf, instead of wetting the surface, and then this droplet really collects any dust which is on the surface of the lotus leaf, and it really ends up going to the core of this particular lotus leaf here. So that is mainly because of the fact that these nano bumps or a nanostructured surface which you got here, it doesn't allow the water to wet the surface because of these bumps. So that's why water can really travel very easily and without wetting the surface. So that's why these surfaces of lotus leaves always looks clean, even during rainy time, and they look very dry as well. So that's why nature is already doing that for nanostructuring and then really creating these so-called hydrophobic surfaces or so. Can we learn from the nature? Can we create the fabrics which don't absorb water, for example? So that means if you spill anything, it won't wet the surface. So that means you're not really ruining your clothes, for example. Also, can we create paints which don't allow the water to wet the surface once if you paint a wall, for example? So any dust which is there, and whenever a water droplet falls from the rain, it collects this dust, and that means you can create the so-called self-cleaning paints or self-cleaning windows and self-cleaning walls. So that can really open up a lot of opportunities. And also, you don't have to use lots of chemicals in order to be able to clean these surfaces, like self-cleaning windows and also non-wetting fabrics and a wide variety of things which people are really talking about. For example, non-wetting surfaces are very good for children, for example, or otherwise elderly patients in the hospitals and a range of applications. So really, the nanotechnology is expected to have widespread of applications. For example, in medicine, and you can do things like a targeted drug delivery for cancer, and particularly for treatment of cancer, the detection of cancer. In the case of information technology, nanotechnology could be used for the giant magneto resistance hard disks, and also molecular switches, which could act like also like transistors. In the energy production and storage, and again, hydrogen fuel cells, and again, fuel cell cars are available, and then people are really predicting in the future, we end up having these hydrogen-based fuel cells, which I'll come back and share with you. And also flexible solar cells and bendable solar cells is something which is again coming up, making use of this nanotechnology. New materials with the lightweight, strong materials, so that means you can build the city-size skyscrapers, and also you can create composite materials which are lightweight but strong for cars and other things as well, which I will come back to. And also in this one, you can have a food, water, and environment. And again, you can make use of nanotechnology for remediation of the pollutants in the atmosphere and in water. And also you can create membranes so that these membranes only will absorb the oil, for example. Whenever there's an oil spill, so then a lot of sea life gets destroyed. And whereas if you can develop the membranes and those membranes are only absorbing the oil, you can much easily clean the water oil spill in the sea and other things as well. But also you need to develop the new instruments, developing the new technology like nanotechnology, and how to fabricate these structures, and then also how do you measure these structures, and that's why people are developing tunneling microscopy, nanomanipulators, and a range of things. So in fact, these are some of the slides which I borrowed from my colleagues Clayton Teague and Tomilini, and from US. Some of these slides are very old slides, in fact. And the nanotechnology is expected to impact virtually all technology sectors as an enabling or a key technology. If you ask me, where are the nanotechnology industries now? And I'll tell you that you will not have any specific nanotechnology-based industry, and then you will have every industry sector will end up making use of nanotechnology. So that's why you should not be looking for a separate industries, but look at every industry which you got, whether it is electronics or communications or computers or energy and materials. And so then you'll be able to see the use of nanotechnology, which I will come back to. So whenever we talk about these things, people always also want to know, is nanotechnology is going to make money? Because see, sometimes governments and people want to ask the questions, their industry or so, and what type of industry growth you would expect. In fact, a company called Lux Research Corporation has really looked at this nanotechnology value chain in 2004. They predicted by 2020, and so here will be the size of the nanotechnology industry or the marketplace with respect to information and communication technologies and with respect to the biotechnology. And they were predicting at that time 15% of the global manufacturing output will be based on nanotechnology. They were predicting $2 to $3 trillion of the economic activity based on nanotechnology. So now this is an old slide, and I can see 2004 or so, but now we are in 2020. Have we really achieved this particular amount of potential revenue which people are predicting? Unfortunately not. The question you ask is why? It so happened till 2008, their predictions were really ramping up and following very nicely. But then in 2008, we had a global financial crisis. And of course, suddenly industries have really been in trouble and the economy was in trouble. And then of course, people stopped investing in the new technologies like nanotechnology because they were gone into the survival mode or so. So that's why we are not ready yet in terms of being able to demonstrate that this sort of manufacturing output is available now. But it might have not happened in 2020. By 2030 or 2040, people are predicting that it's going to happen in due course of time. And again, whenever you got now COVID has come, and again, the economic impacts and societal impacts also have an impact on the industry as well. So that's something as a scientist, we need to keep that one in mind as well. So if the nanotechnology is of so much of interest, how to make nanostructures? There are two main techniques which we use. One is called as a top-down approach, and another one is called a bottom-up approach. And I'll tell you what I mean by that. So you can see the top-down approach is, in fact, for example, a sculptor, and then takes a piece of rock and then really carves whatever the structures which they want to really carve in these ones. So this is exactly what happens when you're really using the top-down approach of making structures. And the silicon chips, for example, made in this top-down approach, and then people are able to really go from millimeter down to nanometer scale or so, which I will come back and talk about. So this is really like a physicists and engineers really mostly look at this so-called top-down approach and lithography techniques or so, which people end up making use of in order to be able to make computer chips or so. But whereas in the case of bottom-up approach, and so in this case, what you do is that you start like a potter, and then you start with the clay, and then start building whatever the structure you want. You want to build a pot, or you want to build a box, or whatever you want to do. You should be able to do that one. And here is an example of the lead glass. And so you can see that in the old churches and other things people have been doing, Romans have been doing that. Essentially, by changing the size of the nanoparticles, they're able to really get different colors, and they're able to embed these ones. These are done from the bottom-up approach. And typically, these things are done by the chemistry approaches sort of thing, so-called self-replicating systems and other things, starting from a sub-nanometer up to 100 nanometers or so. But the scaling to the larger areas becomes much more challenging. So that's why sometimes people want to combine both the top-down and bottom-up approach, so thereby can make use of this so-called directed self-assembly, which can really help from that point of view. So here's an example of a silicon chip. As you can see here, this particular silicon wafer is about 300 millimeters in diameter, about 12 inches. Americans call it as 12 inches. And so you can see that many microprocessors are there. And so like a dinner plate here. And you can really, all these things have been fabricated through lithography processes or so, and highly uniform and highly manufacturable process. You can look at the close-up of this one, and you can look at even more close-up of these transistor structures or so. So the smallest dimensions at that time, which I was preparing this talk, and then it said about, currently we got about 90 nanometer feature sizes. In 10 years time, we'll end up going to 20 nanometers. So now we've already passed the 10 years time. You can see now in 2012, the smallest feature sizes are 22 nanometers, 2014, 14 nanometers, 17, 10 nanometers, 18, 7 nanometers, 2020, we are in the 5 nanometer regime or so. So smaller the transistors dimensions, and faster you can switch them on and off. Also, you can pack more transistors, so that means you can really create a dense memory chips and all these things as well. So already scientists in various laboratories have demonstrated 2 nanometer features transistors already, indicating that in the future we can really be able to really even shrink these transistors much more. That means you can pack more and more billions and billions of transistors on the same silicon chip or so. Okay, you can see we are well and truly in the nano regime. Whenever you're using any of you're using computers or electronics, and we are well and truly in the nanoscale regime. And so it is nothing but nanotechnology. And these are all done from the top-down approach of using lithography techniques so that you can get uniform and large area, and many, many devices simultaneously can be fabricated. And sometimes we also use electron beam lithography. In fact, this is one of the machines in our own laboratory. And what you could do is that you can really deposit some polymer material like a photoresist and come with an electron beam and write the pattern, whatever you want, and you transfer that pattern into the silicon chip or compound semiconductor like gallium arsenide or indium phosphide chip, and then be able to really create whatever the structures you would like to have based on the functionality which you would like to achieve. What about bottom-up approach? And this is the one which typically chemistry colleagues use. And in this case, they take a typical beaker or so, and then they start from the bottom up. So they take some cadmium salts here, solution, and then they heat this one to 350 degrees Celsius or so in the inert atmosphere of argon, and introduce the salts of the solution of the selenium salt. And as at this temperature, once if the selenium salt is introduced, this cadmium salt, they react. And then essentially what you end up creating is that you start nucleating the so-called nanoparticles or quantum dots. And then if they start cooling it, then what happens is that they stop growing, And then also that if you introduce a particular chemical, so then the so-called ligands, so then what happens is that they're attaching to this nanocrystal, and nanocrystal stops growing because it's not reacting with the surrounding media which you've got, sort of thing. So that's how they're able to really control these nanoparticles or quantum dots very precisely. And you can see that a particular schematic of a quantum dot surrounded by these particular ligand structures which stop the further growth of these nanocrystals. So here is an example of the case where these are the results of Professor Munji Bavindi. You can see that these results are about more than 20 years old now. So you can see they've been able to show that by essentially changing the dimensions of these cadmium selenide quantum dots coated with a zinc sulfide, because of the fact that cadmium is toxic, so that's why they try to coat with the zinc sulfide, and also it improves the performance of these quantum dots. And you can see essentially by changing the dimensions, and then whenever the nanoparticle is larger, and you end up getting the red light, and so whenever the nanoparticle is smaller, you end up getting the blue light, and then in between you end up getting the green light and other lights or so. So if you can really produce the primary colors, you'll be able to produce any colors of light which you would like to have. And you can see the spectra they're demonstrating here. And so these structures are really, really small, 1.4 nanometers or 1.75 nanometers, 1.9 nanometers. These are in angstroms, or 2.15 nanometers or 2.5 nanometers. As you can see, by essentially changing these from 2.5 nanometers to 1.4 nanometers, they're able to tune the emission wavelength quite significantly. In fact, these sorts of quantum dots are currently used in TVs and other things as well. So there's another way of making quantum dots. In this case, these are based on the self-assembled growth process of the strained materials. In fact, this is a technique which we use in our laboratory. And we try to grow indium gallium arsenide on gallium arsenide substrates. And then because of large lattice mismatch, you introduce a lot of strain. And then initially, if you deposit about 4 monolayers, a monolayer is about 0.28 nanometers. I'm talking about 1 nanometer or so approximately here. And you can see that the atom layer, like atomic steps, you can see on the atomic force microscope image here. If you add a little bit more material, you end up getting 5 monolayers. And suddenly, this because of the strain, and then essentially the surface energy issues come into picture. And to reduce the surface energy, and they start forming into these islands. If you keep depositing a little bit more material, and then the number of islands are increasing and the size is increasing, and beyond certain point, what happens is that they start becoming into clusters, which we want to avoid. If you can stop this one and then deposit another layer of gallium arsenide, indium gallium arsenide has got a smaller band gap than gallium arsenide, so they all act like quantum dots. And typically these island sizes are about 20 to 30 nanometers in width, height of about 4 or 5 nanometers or so. So really tiny structures. In fact, we demonstrated quantum dot lasers, quantum dot infrared detectors, quantum dot solar cells or so about 15 years back or so, which I'll not have time to go into the details. So as you can see that you can really make these nanostructures either using the top-down approach or bottom-up approach, and then what about applications and what about properties? So as I already mentioned to you, this number of surface atoms are much more, so that means you can be used for catalysis and other things, then optical properties also can change. For example, if you've got the nanoparticles in a sunscreen, are the particles which are micron size, and then they are larger than the wavelength of light, so that means they scatter light, so that's why you can see that you applied something on your face here. But if you're using in the sunscreens nanoparticles, because nanoparticles are so small, the scattered light is not that much which is coming out. But if by controlling the dimensions of these nanoparticles, you can control the band gap of the semiconductor. That means they can absorb only the UV light, but allow the visible light to pass through. So that means you don't even know that you've applied this sunscreen on this side for this person. The surf lifesaver, in Australia, as you know, that there's a lot of UV radiation, and melanoma is a major problem, and we all apply sunscreen when we go out, for example. So if I say that, I'm not interested in sunscreen, where can I make use of? For example, wood gets degraded whenever it's exposed to sunlight because of the UV radiation in the sunlight. So now, if you can really incorporate the nanoparticles of this zinc oxide or titanium oxide of the right dimensions, they can absorb the UV light but allow the visible light to pass through. So that means the wood could be protected for a much longer period. But also people have been trying to make use of these nanoparticles of catalyst materials because of the large surface area and put them into these fuel tanks, and they're able to enhance the catalysis quite significantly. That means the amount of gas which they're using or the petroleum which they're using is much less. So that means you're reducing the greenhouse gas emissions also. And also another property which comes into this at the nanoparticle scale is called superparamagnetism. Say, for example, if we take some magnetic nanoparticles, and then particularly if you go to the nanoscale dimensions, and then you can send these, functionalize these ones, and then send into the brain, for example, where you got a brain tumor, and then you functionalize them such that these nanoparticles are only attaching themselves to the brain tumor, and all other brain cells are not been attached to. Then you apply the magnetic field from outside, on and off. By magnetizing and demagnetizing these nanoparticles, you just start generating heat. That heat is sufficient enough to be able to kill the tumor cells, but healthy cells or healthy brain cells are not been impacted by that one because nanoparticles are in contact with these healthy cells also. So really, without doing surgery and other things, you can really treat people with brain tumor and other problems, which I'll come back and we can talk about more. So what about other applications of these nanoparticles also? So as many of you know that we all use tennis balls, and when you have started playing tennis for some time, and then the air from the balls leaks out, and then you have to, that means there's no more pressure here, that means the bounce goes away, that means we need to go and buy new balls. So what happens is that, you know, these rubber, which they got a small nano gaps here, air starts leaking out gradually. But if you can fill these, in this rubber, we create a composite where these nanoparticles are filling the gaps in the rubber. So that means air cannot leak out. So that means you'll be able to make use of these tennis balls for a longer period of time. And in fact, Wilson, one of the manufacturers of tennis balls, is started already using these nanoparticles in their rubber so that they're, while manufacturing their tennis balls, which can last for a longer time. And also that if you're not interested in tennis, where else can you make use of? For example, food packaging. As you know that the food gets oxidized, so that's why, you know, milk gets spoiled after a week or so, and then other food also starts getting spoiled because of the fact that even they got a packaging here, and, you know, small amounts of oxygen starts leaking out, and then in the process it ruins the food, for example. So can we start introducing nanoparticles the way we're introducing here in this packaging material, so that we can minimize the amount of oxygen passing through this package, so thereby we can make use of this food for a longer period or so. So in fact, people have been really developing these nano packaging materials, and then the key thing which we need to make sure is that these nanoparticles are not leaching out from this packaging into the liquids or whatever it's been stored there. That's very important to ensure that people are not really consuming the nanoparticles and things, other sort of things. So that's something as scientists we need to make sure. And whatever the technologies which we're introducing, they are safe. As you can see, nanotechnology has got lots of applications: protective gloves and A-type food packaging and tennis balls, and developing composite materials also. So now let me come to graphene. As many of you have learned about graphene, and then essentially it is which has led to Nobel Prize in 2010 for physics for Doctors Game and Novoslav from University of Manchester for development of the discovery of the graphene and its unusual properties. So if you take graphite, which has got a one atom layer of graphene on top of the other, it's a very soft material. But if you can peel off one atom layer of graphene and then you fold it appropriately, their properties change quite significantly. And also without folding also, the properties are quite different of this two-dimensional hexagonal lattice of carbon, which is sp2 hybridized carbon atoms. And if you fold them like a ball, you end up getting C60 or buckyballs. In fact, these buckyballs are the ones which has led to Dr. Rick Smalley the Nobel Prize in 1996 or so. But if you fold them into tubes, and these so-called, you end up getting the so-called carbon nanotubes, and then their properties also quite different. And then depending on how you are making use of these graphene sheets, their properties are quite different. For example, graphene is seen as a wonder material, which has got a very low resistivity, 10 to the power of -6 ohm cm, and less resistivity than silver. That means it's more conducting than silver, for example. Okay. Also, the mechanically very strong material, and also that because of this mechanical strength, they can be used for pressure sensors and resonators and NEMS, nano electromechanical systems, And also graphene has got a high carrier mobility. People have seen quantum effects and all sorts of things. And also transverse conductors also. Here's a case of the monolayer of graphene, which you can really see here. And it is transparent because of the fact that the amount of light being absorbed is very, very small because of the very thin layer of this graphene sheet. With the development of the graphene, and so then many people have been looking at what other materials are available. And graphene acts like more like a metal because it's got a zero band gap or so. And by introducing strain, people have shown that they can increase that band gap. And and if you really go for another material called hexagonal boron nitride, and boron and nitrogen organized in the hexagonal format, it acts like an insulator. But whereas if you take the molybdenum disulfide, and it acts like a semiconductor. So you can say by choosing the different kinds of these 2D materials, you can change the properties like a metal or an insulator or a semiconductor. And people are now combining these materials and twisting them one to the other. They're getting lots of exotic properties like superconductivity and all sorts of interesting physics, which is coming to topological properties and things like that. So here's coming back to this carbon nanotube, which I was talking about. This sheet of carbon, depending on how you fold it, the properties change quite significantly. If you fold this carbon sheet here, and then you end up getting the so-called zigzag edges. You can see here, for example. But whereas if you fold it like this, it acts more like the so-called armchair features or so. And zigzag is here, but armchair features are like this sort of thing here. But if you fold it like this, and you end up getting the so-called chiral structures or so. So the properties of these different carbon nanotubes are quite different. Some act like a metallic, some act like semiconducting, depending on the chirality of the fold which you're creating from this graphene or so. And again, their Young's modulus is 1 terapascal, as stiff as diamond, and tensile strength of about 200 gigapascals or so. So really, they got some very unique properties of these carbon nanotubes. Here are some of the examples of the carbon nanotubes my colleagues have created at ANU. And you can see that the electron microscope image of this is a single wall carbon nanotube and a multi-wall carbon nanotubes here. And you can see the close-up of these ones, one carbon atom, one on top of the other. And also you can really get a bamboo-shaped carbon nanotubes as well. And then all these nanotubes have got a different properties. So also that because of the fact that these carbon nanotubes are so strong, and they could also be used to really be able to reinforce the polymers and fibrous materials so that you can really stop the bullet to pass through. So now you can see for people like police and defense people and all these people, and so they want to protect themselves. So instead of having to wear bulletproof vests and all these things, if you can really create fabrics and which doesn't allow this projectile of the bullet, doesn't allow it to be passed through this fabric, which consisting of the carbon nanotubes because of their high mechanical strength of carbon nanotubes. In fact, people can create the composite materials of these carbon nanotubes with other polymer materials. So in fact, A380, this is an Airbus, which is made out of these composite materials, is about 15 tons lighter than if everything would have been used as a metal. And in fact, these wings can flex about 4 meters or so. And because of the lightweight, they can go to long distance despite having more than 300 passengers or so in these big flights you can talk about. But also lighter weight, and then and also and strong. That means the fighter jets and all these things, and they can go and then do a job, and they can come back to the base, and without requiring additional fueling or so because of their lightweight and strength is sufficient to be able to do the task which they're expected to do. So now let me move to other applications. So cancer. I was mentioning to you cancer. In fact, nanotechnology, National Institute of Health in the US has created a National Cancer Institute and mainly make use of this cancer nanotechnology, which they want to make use of, for example, for advanced cancer diagnosis and the prevention and treatment. So they said that nanotechnology will change the very foundations of cancer diagnosis and treatment. So here's a case where people are trying to really show that how you can really be able to really take a particular the cancer drug and be able to deliver it to a particular patients where you functionalize them so that they're only attaching themselves to the cancer cells, for example. So in terms of the other things, for example, quantum dots, which I was telling you, they are very bright. They could also be used to look at the the blockages in the arteries of a mice, for example, they're showing here. If you use a polymer-based the pigments, which typically people used to use, and you can see that the light been emitting is not as bright as that of this quantum dots based ones. So that means you'll be able to detect this any blockages in a much earlier stage or so, and people are exploring these things for real world applications. But also these biocompatible nanomaterials are also very good for bone screws when you get a broken bones or so, and bone bonding starts taking place in 2 weeks, and osseointegration is taking place in 4 weeks. That means cells started growing, and so then cells are penetrating, and then really forming part of our body or so. Also, quantum dots could be used for labeling for various cellular components, which people have been exploring as well. So really, in the biomedical field, there are lots of applications for nanotechnology as well. Here is the work of Professor Charlie Lieber's group at Harvard University, where they were using nanowires, and they are functionalizing each nanowire with a different marker. And so thereby, and you're able to simultaneously detect a different kind, 3 different kinds of cancer. And then as and when cancer molecules are attached to these antibodies, so then their resistivity changes. So in the process, you end up getting different currents. And if the resistivity is increasing or decreasing, the polarity of the current will be changing here. So in fact, if you remove these things afterwards, and then the current flowing through these nanowires will come back, so indicating that you are really able to recover the conductivity quite significantly. There's a lot of potential here to be able to make use of these nanowires for a wide variety of sensing applications. So cancer drug delivery, I was mentioning to you, and again, you can see, you can take polymer nanoparticles with a gap in the middle so that you can put the cancer drug here, or otherwise polymer micelles, or dendrites, liposomes, or viral-based nanoparticles, or even carbon nanotubes could be as a carriers for taking this drug closer to the targeted cells, and then only kill the tumor based on where you need to really kill the person. So that means you will end up having less amount of side effects, and then also you're using a much less amount of this chemical. So that means the cost also can come down quite significantly, and more importantly, the side effects could be reduced quite significantly as well. Here's an example of how people are showing that. So the cell nucleus and the solid tumor here, and then you got the cell membrane, and then how the endocytosis, that means how these capsules can be captured by opening of the cell membrane into the cell nucleus, and then be able into the cell, and then be able to start reacting, and then start killing the cell, for example, cancer cell, for example. So really a very clever way of doing these things. And so people have been exploring this one, and many groups have been working in this particular area. Nanoelectronics. So again, nanoelectronics, and people are predicting that, Hewlett-Packard was expecting the molecular scale version of the transistors, and so thereby, essentially, transistor acts like a switch, and you can also create the molecular switches, which could also open up new opportunities other than just silicon only, for example. So now let me move towards water and energy. So of course, all of us need water, and humanity cannot survive, even the plants cannot survive without water. And again, nanotechnology is expected to create nano filters for desalination applications, for example. If we can create membrane filters where they only allow the water molecules to pass through, any holes which are in this membrane do not allow the sodium chloride, the molecules to pass through, because they're much larger than water, for example. Or water use and recycling for photocatalysis. For example, you got dirty water, you can put some photocatalyst and allow the sunlight to do all the work and stabilize some of this contaminated water into solid waste and things like that. In terms of energy, you can make use of these ones for photovoltaics and thermoelectrics. That means converting photovoltaics is conversion of electricity into light into electricity, and thermoelectrics is heat into electricity. And also people have been talking about hydrogen separation membranes for hydrogen storage, and photocatalysts and materials for fuel cells and supercapacitors, solid state lighting also. In fact, Professor Pradeep in IIT Madras has been really developing some innovative technologies. And so the thing is that he also got some commercial interests and things like that sort of thing. So probably it's worthwhile to both of you talk to each other and then see what is possible and what's not possible. So for example, concentrator photovoltaic systems. So in this case, means people, I know whenever we talk about solar cells, we talk about 25% efficiency or so, and that is true in the case of silicon, for example. But in fact, people have already demonstrated 47% efficient solar cells. These are so-called multi-junction solar cells, which make use of germanium, gallium arsenide, and indium gallium phosphide. And these three different materials have got different band gaps. They're absorbing the different parts of the solar spectrum or so. So they've achieved efficiency of 47%, and these three labs are the main labs which they compete with each other. And only problem here is that the cost of the solar cells is quite expensive, because all these materials are expensive, and also you have to grow one material on top of the other. It becomes an expensive business also. So of course, where can we make use of it? The expense is not where the expense is not a major issue in satellites, because satellite cost itself is so high. People want to have the solar cells which are the most efficient, so that the satellite can last as long as it could, and that's where 3-phase semiconductor multi-junction solar cells have been developed, for example. And also in the concentrator systems, here is a parabolic mirror, and essentially what you could do is that you can concentrate the sunlight here, and you can put the solar cells there, and then you can convert the light into electricity. And again, these are the things which people have been exploring at this stage. How about reducing the cost? And here's an example of the case where you got a germanium band gap, indium gallium arsenide band gap, and indium gallium phosphide band gap. And then, of course, the light above the band gap is getting absorbed, and then really generating the current which is needed in the solar panel, for example. In order to reduce the cost, and we've been exploring to create so-called nanostructures, and then you can also embed them into polymer materials, so thereby you can be able to really create the flexible solar cells which could be attached to the rooftops and other things. And this is the work of Professor Paul Alvisatos and my colleagues in CSIRO in Australia are also exploring these ones. And we are really studying the gallium arsenide nanowires, and then see how things will evolve and how the properties are. So relatively, we are new to these things. And the key challenge is that how do we reduce the cost of the solar panels, say, for example, $100 per square meter at a 17% efficiency to $1 per square meter with a 20% efficiency or so. So that means even the packaging material may cost you more than $1 or so. So that's where the scalability and all those things becomes important, manufacturability and all things become important. Instead of using cadmium selenide nanorods, which Professor Alvisatos' group has been using, we start using gallium arsenide nanowires, because of the fact that our expertise is in 3-phase semiconductors, and then we just want to see how we can really contribute to this particular field. In terms of nanotechnology for cars, and then of course, as I mentioned to you, lighter and stronger materials, lightweight materials, fuel efficiency and safety. You can also improve the engine efficiency and fuel consumption, catalysis, fuel additives, and lubricants, and also the longer service life, lower component failure, and smart materials for self-repair, and a range of things which are possible. And people have been exploring, of course, hydrogen hydrogen cars, and fuel cell cars, and electric powered cars. And we end up probably having a mixture of one technology to the other, at least in the short term, before we can really eventually be able to reach out to the greenies for voting, or otherwise $50. So they just probably send a letter. So sensors in cars. So here's a case where sensors, and you can see that there are many sensors have been used in these cars, for example. So already pressure sensors, temperature sensors, and electronics, onboard electronic sensing, and some more and more sensors have been expected to be used in the cars. And again, nanotechnology is going to play an important role there. So we'll talk about composites. And again, the fuel consumption is very much dependent on the weight of the car. If we can really reduce the weight of the car, we can reduce the fuel consumption also here. And again, people have been talking about 1 gallon, this is one of the American slides here, and can reach up to 100 miles. And if you really reach the curb weight of about 750 pounds or so. So that's what people are predicting these things. How do you really improve, create the lightweight vehicles which are efficient, energy efficient as well. So basically carbon nanotubes, which I'm talking about, multi-wall carbon nanotubes are about 250 grams a kilo, and single-wall nanotubes are about $1 million a kilo. But of course, the prices have come down in the recent times. This is an old slide. But people who want to have the $4 a kilo of the carbon nanotubes they want to have in order to be able to apply for these sorts of applications, because you cannot afford to pay huge amounts of money to be able to create these composite materials, for example. So that's where the challenge comes for us. Can we really not only develop in the lab these things, can we be able to manufacture these things at a low cost? Can we really scale up these processes and other things? And those are the challenges which we all have to deal with. Fuel cells. And again, fuel cells, we have been hearing fuel cell cars or so. In a fuel cell, what you got is two different electrodes, and you got essentially a catalyst here, and then hydrogen comes here, and then hydrogen gets converted into protons by removing one electron at this catalyst here. And then what happens is that you end up having a proton exchange membrane, which only allows the protons to pass through. And then oxygen is going and reacting with protons, and electrons are really lighting the bulb here. And then electrons come here and react, and what you are generating is water. So you start with hydrogen, and you end up byproduct as water. It's a very, very clean energy source. And people have been using platinum as a catalyst, but platinum is very expensive. And my colleagues, Professor Rod Boswell and Professor Christine Charles at ANU, they are plasma physicists. They have really made use of carbon fiber, and they deposited some platinum nanoparticles using plasma processing. They're able to show that the properties of these particular electrodes are as good as that of the planar sheet of platinum catalyst or so. That means it can reduce the cost quite significantly. And also this photon exchange membrane is Nafion, which has been developed by DuPont. And then essentially people are now developing conducting polymers with nanoparticles or so. So thereby they can enhance the proton conductivity of these materials or so. There's a lot of research going on in terms of the fuel cells, for example. So also that people are developing the membranes, molecular sieves, for example. And people are predicting that we will not be able to really jump into the renewable energy overnight. It will take some time. So meanwhile, can we really convert coal into gasify? And then once you can really, because these are hydrocarbons, essentially what you got here. And then you bring the coal and oxygen, and then it's essentially create a gas byproduct. And then you'll be able to separate these things of hydrogen and carbon dioxide. So essentially these membranes have got the holes such that only the hydrogen molecules can penetrate through. Carbon dioxide molecules are too big to penetrate through. So that means you bring in this mixture here, hydrogen comes out here, and then the carbon dioxide comes out here because of the fact that it cannot go through the membrane. That means you're able to separate these things. And people are talking about hydrogen economy, hydrogen-based cars, and a range of things. And we have been looking at splitting of water to generate hydrogen. And of course, if you're using hydrogen as a fuel, you end up producing water again. So why we are not able to do that one of the challenges is efficiency of these processes. For example, if you can take a semiconductor, if you shine this one with the light, and then essentially you create electron hole pairs, and electrons will go here, holes are going and reacting with water, and then creating protons and oxygen here. And then here, you get electrons are coming here, and then these electrons are reacting with the protons, and then you're able to create hydrogen here, for example. So then you got electrolyte here in this particular case. Okay, there's a photoanode and a photocathode, and so then using combination of electrodes or so. And again, we've been exploring 3,5 compound semiconductors as one of the things. And again, some of my colleagues, those are involved in this particular work, for example. So here is a case where people have looked at what type of materials are the best, for example. People typically use titanium dioxide, which has got a large band gap. It can only absorb the UV light, visible light cannot be absorbed. Gallium nitride, same thing. And it's got a large band gap, which straddles the redox potentials of water, but it's not absorbing much light. But whereas indium nitride, which has got a much smaller band gap, and it will be able to absorb most of the light, but it's not straddling the redox potentials of water. So that's why you mix these two and create an indium gallium nitride, and this material is identified as it can absorb more of the visible light, and also it's able to straddle the redox potentials of water, which is the essential requirement for this purpose also. So again, we and others are exploring these particular materials. In fact, this particular slide, I borrowed it from Professor Zetti and me from University of Michigan, for example. Here is a case of the gallium nitride nanorods, which I've been using, though we want to really move towards indium gallium nitride because it's much more difficult to make, and then we have been exploring gallium nitride currently. And by etching these gallium nitride pillars by the top-down approach, we're able to show that the stability issues are a major challenge in this case. And by coating this with a cobalt oxide, we're able to show that we can get a much better stability. Again, we published this work a few years back or so. So what about hydrogen storage? Hydrogen storage is another issue. And then a major challenge is that if you want to really store a hydrogen cylinder, with about 200 atmospheres of pressure, of course, it's an explosive gas, and nobody wants to do that. You can liquefy it, but the liquefaction, you lose 1/3 of this energy gets wasted. So, and then again, people have been exploring lanthanum nickel hydride and magnesium nickel hydride and a wide variety of various materials. And in fact, this is the work of Professor Millie Dresselhaus, who unfortunately passed away recently. She's from MIT. And she has shown that carbon nanotubes, which I've shown you earlier, because of the large gap in the carbon nanotubes, you can store the hydrogen of about 4% at that time, about 20 years back. So now people are able to really enhance the storage capacity quite significantly. So that means you don't use a high pressure hydrogen, and then you can really release this hydrogen from these carbon nanotubes by heating it whenever you need it. And then otherwise it's sitting very close to the atmospheric pressure or so, which becomes much more easier to deal with, for example, and much more safer to deal with as well. In terms of energy, again, batteries. And people have, in addition to fuel cells, people have been talking about batteries. Again, people making use of the nanomaterials and also supercapacitors. Supercapacitors have got a high power density, but low energy density. But whereas the batteries have got a high energy density, but low power density. So by essentially increasing the surface area, by creating the porous materials and of the dielectric, porous carbon and carbon nitride and other things, people are able to really store large amounts of charge, for example. If you're starting this electric car, you want to start the car, that means you need to have a high power density. That's why you can start with a supercapacitor, and then battery takes over, and then you can start driving the car, for example. People are trying to develop the materials which have got both the high power density and the high energy density, so as replacements for capacitors and replacement for batteries, so which will be complementary to these ones or so sort of thing. People have been exploring these ones quite significantly, for example. So here is an example of the case where some of these electric vehicles nowadays, like Tesla and others, have been using, and so they're using some nanoparticles of 20 or 30 nanometers, and they're aggregating them to 1 to 5 microns or so, and of this lithium titanium oxide, a lithium manganese oxide also as anode and cathode. And then the people who want to have about the minimum range of 350 kilometers and recharge time of 3 minutes or so. Already we've got Tesla cars now, again, this is an old slide, are able to do that one, but the challenge is that they can go to long distance, but the charging time is long. So the challenge is that, can we really make long, the capacity of these batteries so that these cars can go long distance, but you can recharge them very quickly. So that's where one of the challenges people are exploring, and a wide variety of research is happening all over the world. And is some of the batteries which are a package state, how they look like. So now let me move towards lighting. So whenever we talk about energy, we also only talk about the storage or conversion, but we don't talk about the utilization. For example, about 20% of the world's light is US light, for example, electricity is used for lighting. And typically people say that 15 to 20% of the world electricity is used for lighting applications. You can see it's US here, Europe here, India here, and Bangladesh is here, and Japan is here, and the Asian countries are here, Australia. You can see that the China and other countries here. And you can see that we are using large amounts of electricity for the lighting applications. So whenever we're using incandescent Edison lamps like this one here, and they're only 5% efficient, so it means 95% of the energy has been wasted. If we replace these ones, the fluorescent LED lights or so, fluorescent lamps like compact fluoro lamps or otherwise tube lights, for example, they're about 25% efficiency also. The LED lamps, which have been recently developed, and now they're already 50% efficiency or so, which people have been developed in the last 20 years or so. So now we are really, in Australia, for example, you cannot really buy the incandescent lamps anymore. All of us are expected to use LED lights or so. That means they're more efficient. And if you can really double the efficiency from 25% to 50%, and then 50 gigawatt power plants are not in the US alone. So now we can see that if we can replace all the normal light globes with LED lights, amount of energy utilization also can be reduced quite significantly. That's something which we should keep in mind. So how to make these white LEDs? And there are two ways you can do that one. You can combine using these materials called gallium nitride, indium nitride, aluminum nitride. And the three Japanese scientists, Dr. Nakamura, Dr. Nakasaki, Dr. Yamano, they've really demonstrated these gallium nitride based LEDs, blue LEDs, which were a missing link at that time. And by combining red, blue, green, three primary colors, you can create white light. Or otherwise, using these materials, you can also create a UV LEDs, and you put a phosphor, like in a tube light. Essentially, these phosphors are exciting the LEDs are exciting the phosphor, and then you can able to connect it the white light. For example, blue LEDs in combination with yellow phosphor, you can also start creating white LEDs and other things as well, sort of thing. In fact, many of my students are really manufacturing LEDs in China, and a few millions a month, and it's really exciting development of this particular material system by these Japanese scientists, those who won the Nobel Prize in 2014 for physics. Also, this LED lighting is now used for agriculture purposes, for example, and for example, in greenhouse agriculture, and LEDs are used for indoor agriculture applications and other things. And also, somebody asked me a question at one of the talks that, where can we use nanotechnology for agriculture? Nano fertilizers, nano pesticides, and nano sensors for measuring moisture and soil nutrients, and a range of applications there. People also talked about microwave photonics and where satellite communications, and again, you're using nanotechnology for making lasers and electro-optic modulators and other things, and where you're able to really transmit the radio frequency signals through the optical fibers, and you're able to really extract the information again, also the so-called microwave photonics. In terms of these things, and my own group, we work on the so-called optoelectronics, and we work on light-emitting diodes and lasers, and for optical communications and solar cells, and also infrared detectors for night vision applications also. Just briefly to mention, this is my research group, is about typically 10 to 12 nationalities at any one time, and typically 25 to 30 people. And so basically what we work on is that we're working on this hexagonal boron nitride, which can really allows the possibility of, I mentioned to you, this much very large band gap material, which could be useful for making UV LEDs. If you can make UV LEDs, and you can be able to clean the water very efficiently, because UV light can kill the bacteria. So by putting an LED light here, then you'll be able to drink the clean drinking water, for example. And of course, the challenge is the efficiency of these LEDs is not as good, and people want to really develop the newer generation so that you can enhance the efficiency quite significantly. Also, that these UV LEDs could be used in the operation theaters and wherever you need sterilization, because UV light can kill the bacteria and viruses and things like that. We've also been making some of the smallest lasers in the world. These are so-called nanowires of gallium arsenide lasers. And then again, I can put about 20 lasers in the width of your hair, so that gives you how tiny these lasers are. Smaller lasers, they can be switched on and off faster. Also, they consume less energy. They could be used for faster communications and sensor applications also. We've also been making nanowire LEDs. And again, I won't have time to go into more details. These are based on this particular material system. And in this case, we are really using these infrared LEDs for silicon photonics applications also. In fact, my student in Suk Yang, who works for Samsung now, he developed these so-called flexible LEDs, because people who want, Samsung and others, want to use these LEDs for flexible phones and other things. So that's why we're interested in exploring some of these materials. We've also been using it for terahertz detection applications, and terahertz radiation is important radiation, which has got fingerprints in many of the chemical molecules. You got fingerprints in the terahertz parts of the electromagnetic spectrum. Terahertz is reflected by metals. You can also look at the cavities in the teeth and for wireless communications, and also look at the water content in leaves, and terahertz is a very important area. So most recently, my colleagues at my former student Kunpang, and who is now a postdoc in Oxford, in jointly with us and the University of Strathclyde, we demonstrated so-called terahertz detectors by putting two different kinds of, like a crossbar-like detectors, and we were able to show that you can really get both the polarizations of light of the terahertz detectors or so. In fact, this work has been published earlier this year in Science or so. Really an exciting time of using nanotechnology for a wide variety of applications, including for metamaterials applications and detection of the signals which are passing through these metamaterials, so that you can learn much more about what are the properties of these particular metamaterials also. Again, we're using nanowires for solar cells, which I mentioned to you. By using this one, you can be able to really, the people have demonstrated from Eindhoven University of Technology, my colleagues, about 17.8% nanowire-based LED solar cells. And we can also be able to make a flexible solar cells, so that they can be used in our backpacks and other things, able to charge your batteries and all these phones and other things. That's our aim in the longer term. Again, this is a joint work with Oxford University. So we have also been exploring nanowires for brain applications, and as many of you know that all of us have got about 80 billion neurons, and then these neurons form into a neuronal network, and then that's how we end up getting the functions. So whenever you got a brain damage and you break the neuronal network, that means you lose some of these functions. So now if we can we create a neuronal patch and be able to really connect them, kind of make these connections back and be able to give the functions back for people, for example. So here's the case. This is the work of my young colleague, Dr. Vinny Gautam, and where she tries to grow the rat neuronal cell and the cell body here on the indium phosphide nanowires. These are all the indium phosphide nanowires. You can see these nanowires here, and about 100 nanometers in diameter or so. You can see these axons or the dendrites really follow these nanowire patterns beautifully, and they show very interesting properties, and that's what we're exploring at this stage. And we're able to show that if you grow this more than one neuron, they form into this nice network on these indium phosphide nanowires here. And Vinny was able to show that these neurons are really communicating very effectively in an ordered and a synchronized network, and we're able to correlate it way or so. So this is really leading to exciting development. And so now we are working on using stem cells of the Alzheimer's patients, and then try to learn about how the signaling takes place in these Alzheimer's patients with respect to healthy people, and so that we can be able to really develop the technologies which will help people with dementia and Alzheimer's and other things, and working with the stem cell biologists in the University of Melbourne and Monash University and University of Wollongong, including computer scientists using artificial intelligence algorithms and other things to be able to develop the various routines for stimulating the neurons and things. So in summary, nanotechnology is multidisciplinary. It's an enabling technology with great implications for the society. Nanotechnology offers exciting science and engineering challenges. Nanotechnology is expected to make a major impact in all industry sectors. But we should always remember that environmental, toxicological effects, and ethical and life cycle issues need to be always considered. Whenever you're developing new technology, we should ensure that the benefits are much higher than the negatives which you got in terms of using these new technologies. So that's our responsibility of developing any technology. With this, I'll finish off with some information. As I was mentioning to Dr. Das, that I started my life in a very small village in India, and I studied in front of a kerosene lamp till I finished my year 7. I lived with my high school math teacher to be able to finish my year 8th, 9th, 10th in a neighboring village because there's no high school in my village. And so as a gratitude to my teachers and parents, and my wife Vidya, and I have started an endowment for supporting students coming from developing countries to visit the ANU Research School of Physics. And then you can look at this particular endowment, type in Jagadish endowment, you'll be able to see the details. And we invite these people for 3 months during summertime. It's a very competitive program. And then basically this is one way to really support the next generation of young scientists. And based on the success of this program, ANU itself has started their own program and really targeting students from the developing countries. Also, there are about 700 African families that have no access to electricity. So again, by donating about 400 rupees, and you'll be able to donate one lamp to the children in Africa, because they're studying in front of the kerosene lamp, which also they're breathing kerosene smoke, which is not good for health. They get very little light. By providing these LED solar lights, and then you're able to get a better light, and also able to study in a good, healthy environment also. Again, education is a very important sort of thing. And many groups are working in terms of really enabling the world. And that's, again, something as scientists and young people, the physicists also, we should always remember that we are in a much better shape than many other people. And what difference we want to make to the world, we should always keep that in mind as and when you're successful in your life. With that, I want to thank you for your attention, and I'm happy to answer any questions you may have. Thank you.
Thank you, sir, for your wonderful session. I have students have learned a lot of things from this session. So now, if you allow us,
sure.
We can start our
very happy to answer any questions, Dr. Nars.
Yeah, thank you, sir. It's a pleasure, sir, to host you, sir. We have already got one guest from Japan, Rafiqul Islam Bhai. So I have connected him. So, sir.
Hello, nice to meet you.
Hi.
Hello.
Good to see you. How are you?
Fine. Thank you, Professor Dr. Jagadish. I enjoyed your lecture, but I could not attend from the beginning, so I missed many things uh, in a short, I can say your all the lectures on nanotechnology. So in a word, we can say that nanotechnology a small solution to big problems. In a short word, nanotechnology now in this all sides of application in this industry or medicine or anywhere we can apply for nanotechnology.
Yeah.
Unfortunately, I am not related to nanotechnology, but I am working on in the medicine side as cancer therapy. But I am
Yeah.
a student of physics, so I am working in the biomedical engineering department here in the Japan of Tohoku
Yeah.
University. So again,
Okay.
nice to meet you.
Good to see you.
Uh, I'm very happy for your lecture that in this lecture you also discussed about the imaging, molecular imaging of nanotechnology and others application of nanotechnology in human brain detections and others. So as we know that now the nanotechnology is a application to the medicine as a nano medicine. So it's a good application. So I would like to request, so as we know that the nanotechnology used in the medicine in uh, many ways. So can you explain in short, what is the benefit of nanotechnology to the cancer detection and cancer therapy or others like that on chemotherapy? How to help this one? Thank you.
Okay, good. Very good question and very important question. So, one of the advantages of nanotechnology is, as I mentioned to you, that the surface atoms, number of surface atoms are quite significant with respect to the number of atoms and the volume of the material. That means these atoms want to react with any of the surrounding medium. So,
Yes,
basically, the advantage of the nanotechnology is that we want to move towards a single molecule detection.
right.
If we can start detecting the cancer at the early stages of development before it metastasizes, be able to can start treating it efficiently, so thereby can reduce the death rate quite significantly because it's not spread in the body quite significantly. So that's why early detection is very important. If you want to have early detection, that means you need to have highly sensitive detectors, sensors, and that means you can be able to look at the single molecule detection, single molecule imaging, and all these things people have been developing using nanotechnology. That's a detection part. In terms of the treatment part of it, as you know that whenever somebody has got cancer, you're doing chemotherapy, radiotherapy, and all these things, people have got a lot of side effects because of the fact that your rest of the body, good cells have also been exposed to all these drugs, for example, a radiation.
Yes,
That means you end up having side effects. So can we really do this targeted drug delivery? You really put in a nano capsule of a polymer material where the drug is. You functionalize that one such that it only goes and attaches itself to the cancer molecule, cancer cells. Then you activate that one afterwards. So that means you're only attacking the cancer cell and the rest of the body is not been impacted. That means the side effects are less, but also you only need a very small amount of drug. You can reduce the cost of that one also quite significantly. So both ways, there's a lot of advantages. So that's why the rest of the people are really working on it, and then many groups are working on it. As you know, whenever you're dealing with nanotechnology for health, we need to make sure after the treatment what happens to the nano capsules which you're sending and all these sorts of things. We need to worry about it as well. So those are the things people have been exploring and making sure that whatever the capsule which you're sending is biocompatible, and also they get out of our system and things like that as well.
Yeah, thank you for your nice and wonderful reply about my not question, it's the discussion. So I am very happy to know from this one. I can just one point add with your discussion. That's presently I am working on the proton beam therapy,
Yeah.
dose verification using the positron emission mammography is a very high spatial resolution and specificity. So presently, we have developed another project for the, you know that maybe the proton boron fusion therapy.
Yeah.
Another one is a neutron proton, that's mean BNCT, boron neutron capture therapy, and
Yeah.
now the new one is the boron proton fusion therapy. So
Yeah.
in this part, if, you know that the proton when interact with boron, then there is a lot of alpha is produced, and the dose inside the um, patient is increased. Here I would like to know if for a brain cancer treatment, so if we use the proton beam, so can we apply the boron nanotechnology
Okay.
for this boron fusion to this one? Have you any idea like that?
In principle, yes. But the only thing which you need to think about is that, in the case of a brain, you always have something called a blood-brain barrier.
Yeah,
So that's where you need to really have to worry about that, how you're able to really introduce the nanoparticles and other things through this barrier. And people have
yeah,
found that if you're using nanoparticles, you're able to really cross that barrier. And I think that's something which we need to also keep in mind when you're doing these things. In principle, yes, but more research need to be done in these things, because
yes.
again, when you're dealing with these things, because whenever you're talking about the human health, in fact, I always tell people the impact of the nanotechnology on human health improvement is much higher, but also it will take much longer time, because you really
Right,
don't want to have any side effects, and also unexpected effects you don't want to have. That's something we want to ensure people are safe whenever you're developing new technologies.
right. Okay, so
Good luck
thank
to
you.
you. Good talking to you.
I
Thank
will
you.
not along your discussion. So let's
No,
go
thank you
for
very much,
your
sir. Good luck to
question
you.
and others.
So thank
Good
you,
luck to
Mr.
you.
Bhai, for your good discussion. So we have a similar question
Okay.
from our student.
Yeah, nice to
So
meet you
that's
again.
okay.
Good to see
Thank
you.
you.
Thank you. Bye-bye.
So,
See you.
so
See
we
you.
can read the question from my student. So does nanotechnology pose a threat to human health and the environment?
Okay, good question. Really important question. Say, for example, this was in fact some of the major concerns we had about 20 years back. In fact, Friends of the Earth, there's a NGO group, they started spreading rumors saying that, oh, well, nanotechnology is going to kill people and we're all going to die due to nanotechnology poisoning and all these things sort of thing. So, but fortunately, those things didn't happen. The reason is, for example, if a computer chip, whether you have got your transistor size is a nanometer scale or a micrometer scale, the properties, it's not going to make a huge impact in terms of your health, for example. But at the same time, when you're dealing with the nanoparticles, because you cannot see them, you can probably breathe those things and it may go and attach themselves into your lungs, for example. So that's why whenever you're dealing with nanoparticles, you should always use fume hoods and other things, and also face masks and other things. So thereby you're not really exposing yourself to that one thing which you need to do so. But most of the nanotechnology, there are no health issues. But whenever you're dealing with the nanoparticles, free nanoparticles, which are floating in the air and other things, and that's where you need to be very careful. But also we need to be careful, and also that's why we always talk about in the area of nanotechnology, you need to, before you start designing a product, safety by design. Don't think of the safety afterwards and then say, oh my God, what will happen to the safety of this? Start from the beginning. How do I make sure that this is safe? The second thing I also want to think about are life cycle issues. Say, for example, I'll just give you one example, right? Well, you're applying sunscreen,
Yeah.
right, using nanoparticles of zinc oxide or titanium oxide. So no problem. I'm not eating sunscreen, but I should not worry about it, right? But then I'm going and washing my face in a water stream, for example. So suddenly, these nanoparticles of this coming from the sunscreen are going into my water stream.
Yeah.
Then there are fish which are start eating these nanoparticles, and tomorrow I'm consuming fish. And suddenly, which I thought is not a problem, suddenly becomes a problem. So that's why one need to be very careful in terms of how you make use of this nanotechnology and make all the precautions. And that's why we call it as a life cycle issues. So once if you make sure that you're really thinking about life cycle issues before implementing any technology, then you will not have major problems both for the environment and in the human health. That's why as scientists, that's why I said, my last bottom slide, I mentioned that how important it is to make sure that whenever you're introducing new technologies, the benefits significantly outweigh the negatives of for the human health or environment or other fellow creatures and all these things. We should always be aware of that. That's our responsibility as scientists, as our responsibility as scientists, because the public trusts us, and we should not lose that trust. For example, gene technology case, scientists lost the trust. And because of the fact that the gene technology case, scientists lost the trust, so that's why gene technology has not been able to be implemented as widely as people would have liked it to be, for example. So that's why the trust is really public. You need to really maintain the trust of the public, but that means you need to be transparent and then make sure you don't do any dodgy things for the sake of money or for the sake of fame, for example. You should never do that.
So thank you, sir. We have maybe the similar question like other the Rufikul Bhai have asked. So which is more safer and better therapy for cancer treatment till now, radiation therapy or nano chemotherapy or nanotechnology use? So which is safer?
So basically, the nanotherapy and other things are not ready yet for the real applications for the human beings. So this is still in the laboratory stage or so. People are exploring on the mice and rats and all these things. So it will take some time. Still, we are now relying on the chemotherapy and radiotherapy or so. But most interestingly, nowadays there is something called immunotherapy. You can make use of immune cells of your own body to fight the cancer, which is entirely new area which has come up recently. That's really revolutionizing cancer treatment and really helping the cases where radiotherapy and chemotherapy, which could not solve the problems. So the immunotherapy is really helping people, and people are able to live longer because your own body is helping you to really develop that fighting capability, for example.
Okay, so thank you, sir. So this is maybe the last question. So we have using the solar cell, but it's expensive. So could we make it cheaper by using this nanotechnology? Is it possible, sir?
Yes, people have been really using, for example, organic solar cells and other things. People are trying to do the printable solar cells, for example, using nanotechnology and things like that sort of thing. For example, I talked about quantum dot solar cells. I talked about nanowire solar cells. And then all these things are coming up now. But the hope is that by using this less amount of material and other things, and we're able to reduce the cost quite significantly. So that's the hope we got. But certainly, for example, if we are able to really develop some new molecules, which are able to really efficient molecules, and you're able to do the printable, like a printer, a laser printer type thing, and you're able to, instead of using ink, if we start using these chemical molecules or so, in principle, we're able to do that one. For example, people are developing perovskite solar cells now. And perovskite solar cells are already 23% efficient. And also, you're only using a small amount of material. You can make them very efficient as well. So this technology is really moving very, very fast at the moment. And the only problem with perovskite solar cells is the stability issue. So that's something, but because once if you expose it to the air, the humidity really starts degrading the performance, and people are now looking at new materials and also trying to put a different sealants and other things so that the humidity doesn't get into the solar cells and other things. And lots of things people are exploring at this point.
So thank you, sir. So as we don't have any more questions, so we should conclude our discussion session. So thanks, sir. We, from the Department of Physics, actually, we would like to say thanks again on the behalf of the Department of Physics from the University of Science and Technology. Sir, we are grateful to you because we know that you are too busy with your research and your other works, but still you give us time for our student. That this is very great things, and we are very grateful to you. So thanks again, sir. And hopefully we'll arrange another program with you. You have already agreed about that. So I'm very pleased about that. So thanks you again, sir.
Okay, thank you, Dr. Pretam Das, and thank you for inviting me. It's always a pleasure to talk to the younger generation. And as I was mentioning to Dr. Das, next time I'm going to give a talk on failures are pathway to success, and I'll share with you all my failures. So that's why don't be afraid of failures. Failures allow you to be able to make progress. Learn from the failures, and you can move forward. And I'm sure that all of you have got a bright future. Good luck to all of you. Thank you very much.
Thank you.
Thank you.
Thank you, also.
Right. Thank you. Thank you, Dr. Salam. Thank you. Bye.
Pretam,